And I'm going to talk to you about, what's happening in AI. I don't know if you've noticed, but it's a thing these days. And we have many people at Google working on this area. So I'm presenting the work of not just my work, but many, many people at Google and elsewhere. So a few observations, which may not come as a huge surprise to you. So machine learning and AI have really changed our expectations of what is possible with computers. If you think back 10, 15 years ago, computers couldn't see very well. They couldn't really understand speech all that well. They definitely couldn't understand language very well. And now we have tools that enable computers to interact with people in a much more natural style because they understand the modalities that people understand and want to communicate with. And along the way, increasing scale of larger amounts of compute, larger amounts of data, and more larger scale models have delivered better results. Nearly continuously for the last sort of 13 or 14 years, this has been the trend and seems to be holding up even today. In addition to scale, algorithmic and sort of model architecture improvements have also provided massive improvements as well. And these two things multiply together, right? If you can have much larger scale and much better model architectures that are able to learn more, per floating point operation, those things together mean instead of 20x from scale, you have 20x from scale and 50x from algorithms, and you end up with a 1000x better thing than you had not that long ago. Also, the kinds of computations we want to run and the hardware in which we want to run them are changing dramatically. So, 4 observations, which are maybe not surprising. First, neural nets and gradient descent. These seem to be key building blocks for how do you actually build truly intelligent computer systems. And they're not new ideas. They're things that have been around for a long time. They were invented in the 70s and 80s. And there was actually a lot of excitement about them in the late 80s and early 90s. I first ran across them in a intro lecture where I was introduced to neural networks roughly like this. We have this kind of nice, very abstracted away version of how we think real life neurons behave, where you have a bunch of inputs, you do some processing, and you decide, are you going to fire or not? And at what strength are you going to fire? And you have connections of these things. And then backpropagation is a really nice algorithm that enables you to adjust the weights on the edges of all these connections in order to make the model behave more in the way that you want it to behave, where you give it a bunch of examples, and backpropagation enables you to make the model learn the behavior you want. So I saw these as an undergrad in 1990, and I got super excited. And I said, oh, wow, that seems like a really good abstraction. It feels like it's a trainable thing, and it can learn almost anything. And at that time, we were not using very large neural networks because we had really pathetically wimpy computers. But I said, oh, maybe if we use the parallel computer in the department, we could train much bigger neural networks, and that would be great. Maybe we just need to use 32 computers instead of 1. And then we could train really impressive neural nets. That would be nice. So I asked the professor who introduced the neural networks topic in one of the classes I was taking if I could do a senior thesis with him, Vipin Kumar. And he said, sure. So I played around with 2 different approaches for training neural networks in parallel. One is, this is what you would now call model parallel and data parallel training. But I called them pattern partitioned and pipelined approach. These speed up curves are interesting, but they taper off because I did the stupid thing. I didn't make the model bigger and bigger as I increased the number of processors. I just made it, much harder to parallelize with a fixed size model. But I sort of filed that away as like, oh, that's an interesting abstraction, and it seems like something I should pay attention to. But then I ignored it for, the next 25 years. Okay, so now I'm going to give you a whirlwind tour of a bunch of advances in the field of ML that have happened in the last 15 years that are really all, combined together to produce today's, most sophisticated models. How did today's models come to be? Well, it was through advancements like the ones I'm going to describe. So the origin of my getting back to working on neural nets at Google was I bumped into Andrew Ng, who's a Stanford faculty member, and in one of our micro kitchens, and I said, oh, what are you doing here? He's like, oh, I'm not sure yet, because I just started a week ago. But my students at Stanford are doing interesting things with training neural networks for speech and vision. I'm like, oh, that's cool. we should train really big neural networks, I said. And so that was the origin, because we actually had quite a lot of computers in those days. And I said, oh, why don't we try training very, very large neural networks? And so we built a software system that enabled us to express neural network and connectivity of those neural networks and do both model and data parallel training across many, many computers. And that enabled us to train neural networks that were 50 to 100 times larger than what the largest ones we could find anyone talking about. We had a way of doing this where we had actually many, many asynchronous replicas of the model, getting updates of what the current parameters of the model were, churning away on their local batch of examples, computing a gradient, and sending it to this distributed set of parameter servers in order to update the parameters of the model. This is, because it's asynchronous, definitely not the right mathematical thing, because in the meantime, the model parameters have moved from the other replicas giving them the parameter servers updates to the parameter model, to the parameters. But it seemed to work, so we were sort of happy anyway, despite it being sort of theoretically wrong. And one of the first things we trained was a very large model to do completely unsupervised learning on 10 million random YouTube frames. And interestingly, we had a kind of a locally connected neural network for computer vision that would use a reconstruction loss. So it would try to take a high-level representation of the neurons at the highest level of the model and then try to reconstruct the pixels that have been given as input. And because that bottleneck layer forced the model to sort of learn higher level abstractions than the actual raw pixels, what we ended up finding was at the top level of this model, some of the neurons had learned to be sensitive to whether or not there was a face of a cat in the image. Some of them learned to be sensitive to whether there was a face. Some were sensitive to is this the outline of a person? All without being told any of these images contained any of those kinds of objects. So it's kind of neat to see that you could learn these high-level abstractions and representations from a purely unsupervised objective. What we could then do is use the initialization of this unsupervised training in order to train with a supervised method to try to do computer vision image classification. And unfortunately, we used the 22,000 category version of ImageNet, which is a more thinly traded version than the 1,000 category one that most people are most familiar with. But we got a 70% relative improvement in ImageNet 22K state of the art by initializing with our unsupervised model and then doing supervised learning on the training set for that data set, which is quite a large relative improvement. So we were happy with that, and we saw that scale really mattered. We also started to do a bunch of work in using neural networks for language tasks. And one of the things we found was that even relatively simple models where you have a vector-based representation of words or phrases, so that you have a nice, 1,000 or 500 dimensional representation of each word or token, and have relatively shallow models. So in fact, we had just the embedding vector, and then we would use the embedding vector of the word to try to predict nearby words. That was one of the approaches we tried. And what we found was that if you apply this to lots of text and use this training objective, you end up with nearby words in the high dimensional space tend to be related ones. So like cat and puma and tiger are all low distance in the high dimensional space, and also the directions are meaningful. So you go in the same direction to change the gender of a word in a gendered language, regardless of what word you start with, king and queen versus man and woman. A year or two later, three of my colleagues, Ilya Sutskever, Oriol Vignal, and Kwok Le, used a neural encoder using an LSTM to essentially be able to learn an encoder for one sequence and then a decoder for a different sequence. And when you initialize the state of the LSTM by running the encoder, that ends up sort of capturing the things that have occurred in that input sequence and enables the model to then use that initial state to then do a good job of predicting the target sequence. So the canonical example use case of this is language translation, where maybe you have a bunch of English-French sentences, pairs that mean the same thing, and the input sentence is English. And so when you're training, you try to decode the French sentence, and you get a supervised learning objective for every token or for every word. And then when you're trying to translate a new sentence, you just use the encoder to encode the LSTM state and then decode from that state in order to produce the translated French sentence. So as we saw more and more success of neural networks, and in particular scaling up neural networks for problems in computer vision, speech recognition, and language, we were starting to both get excited but also a bit worried about how we would actually deploy these much better models. So this is kind of the origin of how we started to create our own tensor processing unit chip program. Is I did this back of the envelope calculation and said, okay, we have this really nice high quality speech recognition model. It halves the error rate for speech recognition, which is a huge improvement. It's sort of equivalent to 20 years of speech research in like 6 months since we started the project by training just a very large, not particularly sophisticated model architecture. It's like a 8-layer fully connected neural net, just trained on a lot of data. And that back of the envelope calculation said if we wanted to deploy this to a scenario where we had 1 billion users talking to this model 3 minutes a day, we would need to double the number of computers Google had. And that didn't seem very tenable for rolling out a better speech recognition system. So that really convinced us that exploring much more specialized computational devices for doing neural network inference and later neural network training was going to be a fruitful path. And so this sort of bootstrap got us to really approach that with conviction and started up a chip design team in order to build these chips. And then the first chip emerged 2 years later, as hardware projects tend to do. They take a little while, but we eventually produced the TPU V1 chip, which took advantage of 2 really nice properties of neural networks. The first is that reduced precision is fine, especially for inference. So you're perfectly happy with about 7 or 8 bits of precision, not 16 or 32 or 64, as most people are thinking about in terms of floating point computation things. And also that nearly all of the models we were exploring were made up of different combinations of a handful of specific kinds of linear algebra operations. Things like matrix multiplies are at the heart of them, and then certain kinds of dot products and normalization and scaling. But if you think about most of the machine learning algorithms of today, different rearrangements of those kinds of operations mean that you can build an accelerator that is capable of very high performance, reduced precision linear algebra, and that can be applicable to a pretty wide range of neural networks. And it's much more efficient because that's all it needs to do. It doesn't need to do anything else. It doesn't need to run Microsoft Word or Chrome or anything else. And so TPU V1 turned out to be 15 to 30x faster than contemporary CPUs and GPUs, and 30 to 80 times more energy efficient than contemporary CPUs and GPUs. And it's also now the most cited paper in ISCA's 50-year history. So we then turned the chip design team's attention to the training problem because we felt like being able to scale up training more than we were able to on CPUs and GPUs was going to be important. And so this is where the focus has been for quite a while. And we've now produced many, many generations of TPUs that are essentially machine learning supercomputers, right? It's more than just a single chip, unlike TPU V1. Instead, it's lots and lots of chips connected with a custom high-speed interconnect that enables us to distribute model training over those chips and communicate both activations and parameter updates and gradient updates across that custom interconnect. Version 4 introduced this funky thing where we have an optical interconnect for racks of these accelerators. So there's a rack of 64 accelerators, and we can make it seem as though that rack of 64 accelerators is right next to another rack of 64 accelerators, even though they're 100 meters across the data center floor. And if that rack fails, we can swap in another rack and make it seem as though this rack is now right next to that one in terms of the net topology, which is important as you get more and more scale, you end up with failures, and so you want to be able to reconfigure things like that. And so we've seen